Okay, in our last installment, we found a very interesting experimental result, and that is that these photoelectron spectra gave us more information about the periodic table and about atoms than we had before. First, Bohr showed us that orbitals help define our atoms by giving us these n equals 1, 2, 3, all the way up to infinity levels, and that would describe the absorption and emission spectra we saw for the atoms. Well, the ionization, though, of an atom to when we remove an electron was measured, and that's what these photoelectron spectra did, these PES spectra did, and they showed us that there was more structure to it than what we'd seen before. There were different type of orbitals. There was s orbitals, p orbitals, and let me introduce the last ones here that we'll talk about, the d's. There's another set called f's. We will mention those later on. So I guess to kind of bring the story into focus, we started with this with the hydrogen atom and Bohr. That's our old energy level diagram. But now we've got to do something different. We've got to take a region of our energy level diagram and split it up. And the question is, how much do we split it up and what do we do with it? That's what we'll get to very soon. But we can label those split ups a little bit better, and we'll give those things a name. Because this is n equals 2 for the oxygen atom that I'm showing right here for the potential energy, or the photoelectron spectrum of oxygen, we're going to label these as the 1s electrons for n equals 1 and the s block, the 2s for the n equals 2 and the s block, and the 2p for the n equals 2 and the p block. If I go back to the periodic table, you can see what I'm saying. Hydrogen is a 1s because it's in the electron, and it's in the n equals 1 right here, and it's in the s block right here. All right, so right here is palladium. Palladium would be in the d block, okay? And so that would be some kind of d orbital is what we would call that. Fantastic. So if we look at oxygen, though, what's interesting about oxygen is if we look at it, there's an experiment that can be done where we can send oxygen atoms through a magnetic field. And oddly enough, they get deflected. So O atoms are deflected in here. And because of that, that tells us that oxygen must be magnetic. Now, if we'd gone through a whole bunch of experiments, we would have found this about magnetic electrons, or about magnetic atoms. Magnetic atoms have at least one unpaired electron. Unpaired electron. That's going to take some explaining, so let's take a look at that. Let's take our energy level diagram for oxygen right here, and let's put it to work for us by putting in the number of electrons. If we think about just the 2s level, okay, we're going to ignore the 1s level. If we look at the 2s level, it's going to have 2 electrons in it. So we would call those paired. All right, and if we look at the 2p or 2p level, it has 4 electrons, and it also appears to be all paired. So in other words, this is not a proper way to set it up. There's got to be more structure to it than what we see. There's just not one 2p, there's got to be structure to it. So let's imagine that there was 2. Imagine there's 2 orbitals that are called 2p. If we do that, lo and behold, we still get all these electrons paired up. There's 2 in each one. All right, so let's go to 3. If we go to 3, this is one way to set up our electrons. If we do that, they stay paired, so this can't be the answer. And lo and behold, if we go here and we set it up just a slightly different way, we put our electrons in a different order. Let's talk about this. What we're going to do is we're going to put one electron here, then we're going to put an electron here, then an electron here. So we're going to fill up each of these 2p orbitals, and then, only then, will we put the next electron in. So this is a very interesting thing. This is called Hund's rule. And all it says is an electron would really rather be in an orbital by itself. And because of that, we can get a magnetic oxygen, 2 unpaired electrons, if we follow Hund's rule. So Hund's rule is pretty much seen as correct. We had hints that there should only be 2 electrons in an orbital because the 1s and the 2s filled up with 2. So what this means is we now have a new piece of information, and that is there's a lot more structure to our energy level diagrams than before, and in any one of these orbitals we can have only 2 electrons at a time. That's it. 2 electrons max. We'll talk more about that later.